We say zero gravity. Physicists wince. On Earth, gravity never turns off. What astronauts experience is weightlessness. They're in continuous free fall, falling around Earth so fast they keep missing the ground. That's microgravity. The forces you feel drop near zero, even though Earth's gravity is still very much there. Put a scale in an elevator that's falling. It reads 0. The mass didn't change. Your apparent weight did. In orbit or any free fall, you, the scale and the room accelerate together so you feel weightless. NASA's definitions call this microgravity. How do we do this without going to space? Parabolic flights. Pilots fly a roller coaster arc. During the top of each parabola, the plane and everyone inside are in free fall for more 20 and 30 seconds. Researchers squeeze whole experiments into those tiny windows. Tourists just float. NASA and Zero-G report. 25 funds. 30 count. 30 seconds per parabola. For pristine data, scientists use drop towers. The Bremen Drop Tower fires or drops sealed capsules down a 120-meter vacuum tube, hitting microgravity as low as 1/1,000,000th of G for several seconds, because air resistance is removed by powerful pumps. It's short, but it's the cleanest weightlessness you can get on Earth. Some facilities don't create weightlessness. They simulate aspects of it. Neutral buoyancy pools, NASA's NBL, let suited astronauts float underwater to rehearse spacewalks. It's not true weightlessness. You still feel drag and hydrostatic pressure. But it's great for procedures and spatial choreography. Random positioning machines, clinostats, slowly tumble samples to average out gravity's direction, useful in biology to mimic some microgravity effects over hours or days, but gravity's magnitude is still 1 G. Stars. Once in a while, physics turns cinematic. In 1997, Andre Geim and colleagues used a Knox-16 Tesla magnet to levitate a live frog. Water, and thus living tissue, is diamagnetic, weakly repelled by strong fields. With enough field, magnetic force balances weight, so the frog floats. That's not zero gravity. The magnet is just counteracting gravity. But it's an amazing way to study processes without objects sagging under their own weight. Zero G on Earth, myths to retire. Gravity varies slightly with latitude and altitude, roughly 9.78 ms2 at the equator and 9.83 ms2 at the poles. That's a 0.5% swing, nowhere near zero, but measurable. Lagrange points in space aren't zero gravity zones. Gravity there is still strong. It's just arranged, so orbital motion stays in sync. Effectively, a gravitational balancing act, not an off switch. We chase microgravity for real reasons. Fluids behave differently. Alloys solidify with new microstructures. Cells sense and respond to altered mechanical cues, and the human body deconditions, bone and muscle loss, fluid shifts, knowledge we need for Moon-Mars missions. On Earth, parabolic flights and drop towers let us build, test and iterate fast before paying orbital prices. So, can you get zero gravity on Earth? Not literally, but with free-fall vacuum towers, clever simulators and the occasional supermagnet, we can cancel weight long enough to do serious science. If you had 25 seconds of weightlessness, what would you test first? Subscribe to BrainRootX for more science that makes the everyday feel impossible.